like I said, we're going to go over some stuff from the two-dimensional problems first before going over that challenging impulse momentum problem. So if you haven't looked at it yet, no big deal. It's still going to be hopefully pretty helpful for you in this particular case. Now, number one, just as it says at the very beginning, is trying to get you to go, hey, this is a practice vector addition problem. That's all that it is. Okay, draw the picture that has arrows to represent the momentum vectors. It should be drawn roughly to scale. Okay, now we've kind of seen this a couple times when dealing with force diagrams versus vector addition, and we saw this on Friday when this occurred. But sometimes when you draw momentum diagrams, like let's say here's the momentum of one initial, here's the momentum of two initial, very similar to our Jim Bob and whoever on Friday. Okay, you usually draw them like this to show where they're going to collide initially. But of course, when you draw a momentum diagram / a graphical vector addition, the main difference is simply this. You take this guy, copy, paste over here, and we take this guy, copy, paste over here. You just draw it on the end in that particular case right there. So this is the same scenario in both cases, except when you want to try to show a momentum diagram / graphical vector addition, there's the total initial in that particular case. Number two says a wide receiver with a mass of 90 kilograms running at 9 meters per second and an angle of 180 degrees. A linebacker tries to tackle that wide receiver just before he was going 7 meters per second at 20 degrees. They stay together as one big mess. Draw the picture that has arrows to represent these momentum vectors roughly drawn to scale. This doesn't have any specific, it doesn't say graphical vector addition, it doesn't say otherwise. So your options are as follows, and they are 100% are options. You can do either one of these. Okay? It just says, hey, let's draw them roughly to scale. Okay? Doesn't matter specifically which one, unless the problem specifically says a momentum diagram. If it says a momentum diagram, basically just do it like a vector addition in that particular case. Does that make sense? That being said, okay, it might be easier to draw it this way in order to tackle part B. The reason why these guys switch where they're going at all is because of, as we said at the very beginning, which of Newton's laws are we pretty much reliant on here to look at momentums changing? Newton's third. Okay, so if this is, say, let's switch colors here. Let's go to light blue here. Part B says, draw the force diagram on each object, specifically drawing the third law pair. Now, if this is a wide receiver and I'm not doing the exact angles or whatever, I'm just using my kind of sketch in this particular case. So person one, person two. Remember when we talked about the other day, these are really viewed from the top down. Okay, so technically, which way should gravity go? It's a top-down view. Technically, which way should gravity point? Into the board, right? I'm not asking you to draw that. I just want you to kind of like wrap your mind around technically where it would be. Also, we would probably have a force normal, which would be in what direction? Yeah, so I'm not worried specifically about the up-down in that case. I think that can cause some confusion. Like it says on there, the main thing we're worried about in this particular case is the Newton's third law pair, just like we saw with two guys running into each other. So how do we do that in 2 dimensions? Well, what's happening here is, right, if I run into the shoulder of somebody else, they're pushing me this way, and Newton's third law says I simply push them the opposite way, right? So here they are running into each other. So I would say, okay, which way is 1 going to push them? Here is the force of 1 on 2. Okay? Sort of arbitrarily chose this direction, like they're going to run into each other evenly. But if that's the force of 1 on 2, what's going to happen then? Here's the force of 2 on 1. And that's all I'm looking for. Any questions on that? I'm not really worried about gravity. I'm not worried about normal or friction, or specifically highlighting this Newton's third law pair. So this picture right here covers both A and B on all of these situations right here. Does that make sense? To get part C, okay, what we talked about on Friday, how do you get the individual momentum of these guys? P equals mv, correct? Here are your steps, essentially. Okay, if you are struggling at all on these, I'll give you a series of steps. How do I do these? Number one, you go for individual momentums, which, like you said, is P equals m times v. The same angle of the velocity is the same angle of the momentum, right? Then step two. Really, there's only step two. Once you have these two individual momentums that are both vectors, how do you get the total of them? Vector addition. Vector addition will get you the sum of momentums initial. And that really answers part 3 on here. Now, I'll talk briefly about number 3 here, but it's almost the exact same thing. Number 3 is almost identical to number 2. Okay, you've got these two guys. Heads up, you do have newtons here, right? Do we really want newtons? What is newtons a measurement of? That would be a measurement of force of gravity, right? So what are you going to need to convert that to? Well, actually, no, you don't need to convert it. My apologies. Because it's in newtons. That's force of gravity. What do we really want? For momentum, we want mass. So all you got to do with the newtons is what? Divide by g will get you mass, and then you can proceed like normal from there. All right. From that, you do steps 1 and 2 identically, right? Find the individual momentums, add them all up. And the final question on number 3 says, hey, what's the final velocity? Well, simply, how does the initial momentum compare to the final momentum? Just conservation of momentum right here. And I'll save number 4 for number 4 on here. The only thing that changes about number 4 is this. It says a nerdy young Spainhour is walking down the hallway at 4 meters per second at 270 degrees. Okay, and a penguin bully stands starting at rest, sees the nerdy Spainhour and pushes him. After the penguin pushes Spainhour, Spainhour is traveling faster at 253.2 degrees, separate from the penguin, so they are individually the same. So what we should do here is, here's Spainhour before. Penguin is just standing there, so here's the penguin before, right? Then, what is Spainhour doing afterwards? Well, like I said, going faster, so with more momentum, down and to the left. So see if you can't tell me this. Where would you expect the penguin to then be moving if this is the case? Up and to the right. Now that's the way they would go. How could we get that? Well, this blue right here is the total initial momentum. This is the momentum of Spainhour final. So this would have to be the momentum of the penguin final, so that both of the two of these arrows are exactly the same. Okay? To collectively, I'm not going to spend too much longer on this. I've kind of solving the problems for you to a certain degree. But just to give you a picture of essentially what happened, okay? I'm walking down the hallway. We called this 270 degrees. And afterwards, I was going faster, and in this way, you should be able to use that momentum to predict where was I shoved from. If I'm going faster, and now that way, where was I probably shoved from? Probably as I was passing, it probably pushed me somewhere over there. Yeah. Does that make sense? Good. And honestly, you can kind of use my final momentum to make all sorts of basic predictions based on that, right? If I had said, okay, Spainhour was walking down the hallway at 4 meters per second, and afterwards he's now going backwards that way at 4 meters per second, well, then which way was he shoved from? Well, there was someone standing in front of him, and then shoved him a little bit to the right in that particular case. Does that make sense-ish? Okay. All right. I'll let you work on those tonight. I'm not going to go too much more. If you are stuck tonight, tomorrow, of course, being when we usually go over questions before the test, I will do all of the problems that you want me to do so that you can see them. Ideally, though, as always in here, I would prefer you get stuck on a problem before I just straight up do it. because that kind of defeats the purpose if I just straight up do it. I do already know how to do these problems. So you got to figure it out yourself. All right, let's move on unless there are any questions further about this. Do you feel more confident with your ability to do this now, or you don't have to placate me? If the answer is no, like, we feel about the same, that's good to know as well. All right, let's move on to the challenging momentum problem. As previously mentioned on the last problem, I'm not trying to be self-referential. I'm trying to make fun of myself, although there's a fine line there. Anyway, I am a ridiculous nerd, and I'm a big fan of D&D. So I'm going to use a D&D reference in this particular case. I would 110%. Freaking nerd. Although you guys are all in here, so. All right, pot and kettle. All right, moving on. Here's a person running through a dungeon from. Well, sorry, hold on. Let's get particular here. What level is the person?
5.
5. All right. Okay. So they hit their first bit. So level 5 human. Okay. All right. How fast is this level 5 human running?
5
No. The correct answer was 30 feet a second. Come on, D&D kid, you got this. Okay. 30 feet a second. If you didn't know, every question or everything takes place in like. Is this? No, it's not 30 feet in a second. It's 30 feet was it 6 seconds? It's 6 seconds. Every turn is 6 seconds. Yes, my apologies. So they should be going at what, 5 feet a second, which puts them at what's that? I'll round it. 1.6 meters a second is how fast the level 1 human's going. Okay, they are doing this because they are pushing with their muscles. How do I want to do this? Let's go. Oh, no. Let's not go to 1.6. Let's not give you that. Let's say they're pushing with their muscles at, well, I'll decide that in a second. How big are they? 100 kilograms. Okay. Okay, the force of their muscles is 320 newtons, and we're going to say it's frictionless right now. No, not 320. Not 320. I'm sorry, I'm making this up. I'm trying to make numbers relatively accurate. 160. Push it 160, and we're going to say no friction in this case. No friction. This particular case. All right. Then they run into a gelatinous cube. For those of you that are not giant nerds in here, they're way too low level to be running up against a gelatinous cube. But more importantly than that, if you don't want to nerd it out, imagine that there was a giant amount of Jell-O that a person just ran into. There you go. Stop. That's essentially what's going to happen in that particular case. Okay, and they're going to hit the Jell-O. And how much time before they stop? So let's not do a second.
All right.
We'll do less.
Half a second.
Let's go. Let's make it a little bit more. 0.4 seconds. Okay. 0.4 seconds to stop. I think that's all I need. I might have to come back a little bit later, but I think we're good. The question on the table is, how much force does the cube put on the person? Now, I've already told you ahead of time that this is a impulse momentum problem. But let's go back to a conversation we had the other day. What about this problem in general really should steer you in the impulse momentum direction anyway if this was on a test and I don't tell you, I don't prompt it? What's that? No. I could see it being the hint right there. But you remember we talked about the other day, I put this up on the board because this definitely is a separate problem I know is 100% on there. The situation was the two people that you said ran at each other. And I said, looking at the exact same situation, how do we look at this so that we know it's impulse momentum? And how do we look at this so that we know it's conservation of momentum?
There's only one person
There's two people, and it's the same scenario. Sure, but I don't think the problem is inherently going to tell you that. So what about this? What are we looking at that we would use impulse momentum? And what are we looking at that it's conservation of momentum? To give you a little bit of a hint, I told you about systems in this conversation and how you decide the system is the answer to this question. It's the same situation regardless. I can use either one of these. And as a matter of fact, this scenario I used for both of the two of these. So how do you know which to use? Yes, Aiden.
Wait, is it when we know like two like information for both of them? Is that
Sort of. Let's say it differently, okay? When I walk down the street or whatever, does reality have to guess which one of the two of these to use? No, it uses both of them. 100% both of these things are true. So when do you know to use one versus the other? All right, I got you. We'll go over this again. The only reason I'm doing this to you guys right now and drawing this out is I want to be very clear. We have already had this conversation, okay? Which is fine. I have no problem repeating it again. It's the reason a teacher would stand in front of you and be like, this seems an important thing enough to talk about it again, and it's not great that nobody knows. It's how you define the system. And the way we defined the system the first time was we simply looked at one person. And when we looked at one person, the answer to this ultimately is, what do you look at to decide which one to use? Sum of forces. Okay? What would the force diagram be on this left person running to the left? Yeah, force of gravity. Force normal. Okay? Let's not worry about that right now. Okay. When they hit, though, there was another force. There was the force of whatever we decided. What were their names again? I can't forget.
Jim Bob and Stitch?
Stitch, right. So this was the force of Stitch on Jim Bob. Okay? And the answer to that question is this. If you look at that circle, is there a net force on that circle? Yes. Which direction? To the right. So will their momentum change if there's a net force? Yes, it will, to the right. We don't know if Jim Bob necessarily is going to slow down or turn the opposite way, but we talked about that by changing the mass slider, sort of by substituting Jim Bob for a small child of mine to try to show that discrepancy. Either way, regardless of who it is, they're going to be pushed back the opposite direction. The switch comes, okay? The switch comes when you did that originally. When we looked at that originally, I had not even drawn that person, but I did comment that they were definitely there. Yes? Now, you put them back in the scenario. Now we look at this system instead. The Stitch Jim Bob system. And if we do the force diagram on Stitch, here it is. If I add up all of those forces right there, is there a net force anymore? No. The net force is now 0. So will there be a total change in momentum? So let's say this correctly. Will they individually change momentum? Yes, because individually there's a net force on each of them. But collectively as a system, is there a net force on them? No, and therefore will their momentum change in total? No. Okay, this is, and that's why we got to this, the conversation of why it is that I can't throw a force myself to get myself going in space, right? There's the conversation. I can't take my arm and go that direction in space. Why not? What's the system we're trying to move? What's that? The whole of me, correct? But what I did is I put a force on what? Not just me, be more specific. I put it on my arm. I put a force on Spanauer's arm that way. For the rest of Spanauer, put a force on Spanauer's arm. Newton's third law says what has to happen? The arm has to put an equal force on the rest of Spanauer this way. So the net force on Spanauer is 0. You cannot move because of an internal object. Something must be external. To get morbid, like I always seem to do, if I then cut off my arm and through my arm, could I get myself to move? Yes, because now it's external, something is leaving in that case, so sure, I can get going in that particular case. So again, if I look at an individual, there is a net force, change in momentum. If I look at the total, which sum of force is now 0, and therefore there will not be a total change in momentum. Now, can they individually trade around? Sure, and they do, but all the initials will equal all the final. Or here's another way to put that if you prefer this way. On this second equation, in this second equation right here, the total change in momentum is 0. You add up all of them and you get 5, and you add up all of them at the end, you get 5. There has not been a change between these two. All right. So, that being said, back to here. How do you know which one to use then when you get to a problem like this? You're looking at an individual person. Is there a net force on that person? Yes, there is a net force on that person. Since there is a net force on that person, will their momentum change? Yes. There's a different net force when they run into the gelatinous cube, but still, there's a net force, and so it will change. All right. What time are we at? I'll decide how much to let you do and how much to let you. All right, so here's the question. The force of muscles on this person is 160 newtons. They have a mass of 100. We're going to say no friction in this particular case, and the question is find the force that the cube puts on the person once they enter. Which way should the cube push on the person when they enter? Yeah, back to the left. Just doing a quick force diagram here. Here is the, back to yellow. What's the force diagram on this person? What's that? Gravity. Okay. Normal. Muscles on person. We're going to say that this force of muscles on person doesn't go away when they hit the gelatinous cube, by the way. They're going to keep pushing. Even though they keep pushing, they aren't going to stop. Does that make sense? So what is the force diagram then when they get over here? Force of gravity. Normal. Well, and I said the muscles aren't going away. So force of muscles on person. And should it be bigger, equal, less? Bigger because? Not quite. They're stopping. Correct. Cube on person. So that's what we're looking for right there. Okay? So let's go ahead and see if you can't do this problem. Let me give you a 5-minute head start on me. Yes.
Make it nice.
Sure, have fun. Ooh, let's do this. Sorry, one more piece of information I realized I just need. You need the distance to the cube. We'll say they start from rest 2. You too. Point at meters away. Correct answer is 560 Newtons. Do you guys feel like you're making progress and need time, or do you want guidance? If you're making progress, I'm going to give you time. If you feel like you're stuck, I don't want to leave you just stuck. Let me tell you what I did, so in case you are stuck, or maybe you can kind of confirm. First thing I saw with mass right here is I wanted to figure out how fast it was going once he hit the gelatinous cube. I was given this 0.8 meters, and I did say a second ago that he starts from rest. So that means I'm looking at maybe for some kinematic variables. The first thing that I did is I used sum of forces to get acceleration, right? Once you have acceleration, you have 3 kinematic variables. Once you have 3 kinematic variables, you can then find the speed that you hit the cube at. So if you just do sum of forces in the x equals mass times acceleration in the x, this should just be force of muscles on person, because we didn't do friction, right? Is equal to mass times acceleration in the x, which would just be 160 newtons divided by 100 kilograms. So acceleration is 1.6 meters per second squared. Does that make sense? Okay. Then, if you go velocity initial is 0, velocity final, we don't know. That's what we're looking for. By the way, velocity initial and final, let's be clear. Velocity initial is how fast he's going here. Velocity final would be how fast he's going there, while his acceleration is 1.6. You got to be careful of this because some people get confused. Shouldn't velocity final be 0? Velocity final would be 0 at the end of this section, right over here, not at this section where he should be going pretty fast before he hits the cube. Yes? So we know acceleration is 1.6 meters per second squared. We know that displacement is 0.8 meters. Yes? So from here, relatively basic kinematics problem. Velocity initial is 0. So the square root of 2a delta x is velocity final, which would be 2 times 1.6 meters per second squared times 0.8 meters. Square root the whole thing, and you actually should end up with 1.6 meters per second. Which, by the way, I was trying to do math in my head to just get them to be 1 second, and then I realized I didn't want to give you the time, blah, blah, blah. It's not important behind the 8 ball. That's why numbers are ending up a little bit weird. Now, you might notice correctly, Spain, we haven't dealt with impulse momentum theory at all. We sort of do, okay? We sort of do here because this, if you'll remember, is impulse momentum theorem. Now, what guided me in this particular direction right here is the fact that if I had instead started from here with the impulse momentum theorem, I'm trying to get velocity final, and I don't know time in this particular case, which tells me, hey, I probably shouldn't be using with this guy right here. As opposed to when we enter the cube over here, it says we have 0.4 seconds to stop, which are 2 kinematic variables in that particular case. So let's go from here, okay? Here is the impulse momentum theorem. Okay, so this sum of forces is a result of the cube plus the muscles on person at that particular time. Okay, that time is 0.4 seconds. Be careful of the change in momentum. Before you do anything, make sure you split that up into momentum final minus momentum initial. One confusing thing about this problem is that the initials and finals sort of switch, right? We went from here at rest to 1.6 meters per second right there. Yes? That 1.6 meters per second, when you do this section, the cube section, is that the initial or the final? That would be the initial. What is the final momentum? So when you come over here, you would cancel the final momentum, and I'll be able to check if you understand this because I'll still see a negative left over because it should in fact decrease their momentum. How do I get that momentum initial? How do you get any momentum? So this would be mass times velocity initial. Okay? And then I would get sum of forces by dividing by time. Now, technically, right now, this is exactly the same as we have done in previous stuff, sum of forces and all that. Here's the only major switch we're going to make. And it's a very similar one to what we did over here just a second ago. How do you do the sum of forces when there are individual forces, right? Well, let's do a quick aside real quick, okay? If I said that someone was falling, here's force of gravity, here's force of friction as they fall through the air, okay? And force friction isn't as big. And I asked you to sum the forces in the y. What would you tell me? What is the sum of forces in the y in this particular circumstance? Assuming this is, you're just doing the equation, and we don't know they're the same. What would you write if I wanted the equation for the sum of forces in the y here? Correct. You do force friction minus force gravity, which this is simply just the vector addition of both of these in order to get the total, right? It is literally the same thing here. What is the sum of forces? Well, let's start with this. Do we actually care about the y right now? So this is actually the sum of forces in the x. So how would you write down the sum of forces in the x in this case? Perfect. And from this, the rest of the problem is relatively simple to finish. We are just finding this guy right here, right? This guy right here. So to find that, I'm going to add it over here. Okay. And I'm going to add this at the same time. So I have force of muscles on person plus mvi over delta t. What is the force of muscles on person from the very beginning? 160 newtons. What was the mass of the individual? What was the velocity initial heading into the Q? 1.6. And how much time did I say it took to stop them in the Q? 0.4 seconds. 160 divided by 0.4 should be the same thing multiplied by 2.5, which would be 32400. That's 400 plus 160 is 560 newtons in that particular case. So, as quote-unquote challenging as this is, the reason I put challenging is similar to a lot of stuff in momentum. There is arguably nothing new here. That doesn't make it easy, though. Please make sure that you don't feel like I'm trying to condescend when I say that. We regularly have to have this conversation in physics, too, where I accidentally use the phrase, oh, that's easy. If I ever do that in here, I want to be very clear what I mean. Okay, if I say that's easy, that's not me being condescendingly like, Spader, you've been doing this 18 years, of course it should be easy to you. Of course it should be easy to me. If it's not, I shouldn't be your teacher in that particular case. If I say something is easy, what I am trying to say to you is, I know for a fact, having already tested you, that you have all of the skills for this thing. You just aren't looking at it maybe from the right perspective. It looks more different than it actually is. Are all of you capable? Let's just go through this piece by piece. I know it's not easy, but piece by piece. Do you think you're all easy to find sum of forces to get acceleration? Arguably, this is a relatively basic one. Yes? Are you all relatively okay to do one-dimensional kinematics in this particular case? Yes. Okay, even the quote unquote like hard and new thing of identifying that the sum of forces is just this, pretty sure all of you are very capable of. Now, putting that all together into the same thing, not necessarily easy, but you do have all the individualized skills. Give me a fist of 5 your ability to replicate this on a test. Okay, I can almost guarantee something like this will be more close to beyond the test than the simple version. You will get practice on the review. It's already on there. Okay, just keep working and we'll be okay. All right.